Imagine standing beneath a dark sky filled with shimmering stars, trying to picture tiny, unseen travelers drifting quietly through the cosmic void. The panspermia hypothesis suggests that the origins of life on Earth and perhaps other worlds might trace back to microscopic organisms or basic building blocks of life that journeyed here on asteroids, comets, or dust grains. It relies on the idea that life, or its chemical precursors, can survive interplanetary or even interstellar travel, arriving intact on a planet's surface. I recall reading about experiments where scientists exposed hardy microorganisms like certain bacterial spores and even tardigrades to the vacuum of space. In those tests, some survived intense radiation and temperature extremes, returning home alive. These findings have not confirmed that panspermia occurred, but they show that survival in such harsh conditions is not always impossible. There are records of meteorites carrying amino acids, the basic building blocks of proteins, discovered after falling to Earth. I remember feeling a strange surprise when I learned that these chemicals, essential to life, don't have to form solely on our planet. Seeing images of scientists carefully slicing meteorites in sterile labs and detecting organic molecules inside felt like witnessing a quiet revelation. These amino acids existed before humans even dreamed of searching for them. In the early 20th century, researchers proposed that Earth's first living organisms might have arrived from space. More recently, the arrival of space probes like Stardust and Rosetta, which sampled cometary material, reinforced the possibility that essential ingredients for life are widespread. I remember following coverage of these missions, feeling a flicker of excitement each time new organic compounds were announced. The presence of sugars, amino acids, and other building blocks suggested that what we consider special on Earth can also be found drifting across cosmic neighborhoods. In Antarctica, scientists recovered meteorites believed to have come from Mars. Some of these rocks contained structures resembling tiny fossilized microbes. While heated debates followed over the interpretation of those shapes, these meteorites demonstrated that planetary ejecta can travel vast distances and land on other worlds. The image of a rock flung from one planet, wandering through space for millions of years, only to settle onto another planet's surface, once made me grin at the sheer improbability of it all. Yet there it was, sitting on the ice, waiting for someone to pick it up and examine it under a microscope. I recall reading about the concept of Lithopanspermia, the idea that life tucked safely inside rocks might survive violent ejections from a planet's surface, endure the cold emptiness of space, and finally arrive somewhere else, intact and ready to flourish if conditions allow. Researchers fired projectiles into rock samples, simulating cosmic impacts, and found that some resilient cells remained viable. The notion of tiny hitchhikers riding aboard interplanetary debris seemed both comical and awe-inspiring, like stowaways sneaking onto a grand cosmic cruise ship. Observations of comets and asteroids often reveal a wealth of organic compounds. I once read a report describing how certain complex molecules found in meteorites can form rings and chains that resemble early life chemistry. Witnessing scientists announce these discoveries made the whole idea feel less like distant speculation and more like a plausible scenario. Not proof, but a scenario that simply cannot be dismissed out of hand. The panspermia hypothesis includes multiple variations. One proposes that microbial life itself travels fully formed between star systems, while another focuses on simpler organic precursors. Some suggest that radiation pressure or stellar winds might push tiny particles across light years. The details differ, but the underlying premise is that the seeds of life don't need a single cradle. They can drift through space until they find a suitable home. There's the concept of directed panspermia, where an advanced civilization could deliberately send life forms to seed other planets. While no direct evidence supports such actions, the mere possibility sparks curiosity. The image of some distant intelligence carefully packing microorganisms into capsules and launching them into the void to ensure life spreads through the galaxy is hard to forget. Though this idea belongs more to speculation than confirmed fact, it highlights the breadth of what panspermia could encompass. I remember feeling amused when I first learned that even the upper atmosphere of Earth might occasionally collect and filter out microbes that come from space. High altitude balloon experiments recovered strange particles, though debates ensued over whether they originated here or not. Whenever I read about these claims, the thrill of the unknown pulled me in, even though the evidence remained inconclusive. In practical terms, panspermia stands as a testable idea. Future missions to Mars, Europa, or Enceladus might find familiar life forms, organisms with DNA or RNA close to our own. If that happens, panspermia would rise on the list of plausible explanations for these similarities. Until then, the hypothesis remains a patient visitor in the scientific discussion, waiting quietly as telescopes improve and space probes gather samples from distant worlds. Some researchers note that if panspermia is common, life could be more widespread than we imagine. But the hypothesis doesn't require that life must be abundant. It only states that if life or its components travel between worlds, then Earth's biochemistry might owe a debt to distant corners of space. Standing outside on a calm night, contemplating specks of light that represent countless unknown destinations, it's easy to feel empathy for the fragile microbes that might have journeyed across those gulfs. The sheer persistence and resilience required to endure such voyages can evoke respect, even if we have yet to prove any of them actually made that trip. Panspermia does not explain the initial origin of life, nor does it demand that life must have come from somewhere else. It offers a different perspective, a way to think about life's distribution rather than its genesis. It invites surprise at the resilience of life's simplest forms and awe at the chemistry hidden within space rocks. Whether or not panspermia ever occurred, the idea challenges us to see our planet not as an isolated exception, but as one node in a vast cosmic network of matter and molecules.